On muscle fatigue, here we demonstrate the effect of continuous contraction in muscle fiber and the development of fatigue. And we want to know what effect does a series of stimuli at different frequency have on muscle contraction. For the analysis, we are going to measure the time after stimulation and then put the value, the force of contraction into this column for either nerve or muscle. Since we stimulated the muscle, we're going to fill in this column. We are still going to be utilizing our marker tool, our DVM time. So this is the beginning of the experiment. Fatigue. For example, when a farmer works for 5 hours non-stop, he becomes weak and tired. This means that fatigue has set in. He regains strength after relaxation and replenishment of nutrients to continue working. So similarly, when isolated nerve muscle fibers are repeatedly stimulated, the muscle become weak and exhausted. If the parameters are measured, it will show progressive increase in latent period, progressive diminution in height of contraction. There will be progressive diminution in height of contraction. As you can see, we start with the highest contraction and you can see how it is coming down, and progressive decrease in period of contraction and relaxation, and that is why it's giving us this kind of shape. And studies shows that muscle fatigue increases in almost direct proportion to the rate of depletion of muscle glycogen, adenosine triphosphate ATP, and oxygen with build-up of carbon dioxide. Prolonged muscular exercise causes fatigue, which may be linked to central phenomenon in the brain and spinal cord. Therefore, tiredness of the muscle is what is known as fatigue. So, site of fatigue could possibly be established in seat of the neuromuscular apparatus, namely the nerve fiber, muscle fiber, neuromuscular junction, and nerve cells of the central nervous system. And for the analysis, we are going to be measuring at different intervals the height of contraction from 1 second, 5 seconds, 10 seconds, 15 seconds, 20 seconds, 25 seconds, and 30 seconds. Let me just put it here very close here so that we know the height of contraction in 1 second. So in 1 second, we are also going to bring out our force DVM at 1 second. As we move 325.24, 325 muscle, 325.24. We move to 5 seconds. 5 seconds we have 245.22, 245.22, and we keep on progressing 10 seconds, 239.54, 239.5. All right, 239.54 at 10 seconds. So the next one is 15 seconds. At 15 seconds, what do we have? 254.77, 254.77. At 20 seconds, 233.35. At 25 seconds, this one is an artifact. So at 25 seconds, 200.82 milliseconds. 200.82 milliseconds. Then at 30 seconds, what do we have? 191.79. So you can see progressive decrease in height of contraction. So after imputing all your values on this table like this, you're going to be plotting a graph of force of contraction over constant stimulation. So the next analysis is to determine the time of maximum force and the maximum force of contraction, and then force at the end of the contraction, and then the force at end percentage of maximum. I will show you briefly how to go about that. I've already done it, but I will be repeating it with the marker tool at the same position, at this same position. So we record the time of maximum contraction. We have 326.53 millinewton, which we entered into the table. See it here, and this is the time. So, and the time at the end, we now moved our cursor to the end of the contraction. Let me expand a little bit to the end. Let's move our marker tool. When you put the marker tool here and you measure the height of contraction, you have 56.01. So this is it, 56.01 is on the graph. And then on the table, we do a simple calculation, percentage of maximum, which we got 17.5. This we divide 56.01 over 326.53, 56.01 divide by 326.53 multiply by 100. So we got 17.15% percentage of maximum. So that is how we got our results. And then we're going to use this to as a guide for our discussion, and then plot a graph of force of contraction over time with constant stimulus using this table.